Hello, good day. Welcome to Lecture 5. In Lecture 5, we are looking at applications of centroids, centers of gravity, and centroids of volumes, or 3D centers of gravity and centroids. Right, the applications of centroids and centers of gravity that we are studying are called distributed loads. So when we're talking about distributed loads, basically what we are referring to are structures in which we have some material on top of some support, and then that material is distributed. Sometimes it can be distributed uniformly, but in reality it's always non-uniform. So we will need to analyze the weight in terms of the weight per unit length along whatever geometry the support looks like. So in this study we are extending now, right? We're extending from chapter from lecture 4. If you still remember, we found means and ways of calculating centers of gravity and centroids, but these were in 2D. So we are now moving from 2D to 3D, and the 3D case is discussed in this. So let's first look at applications of centroids in 2D, and then we will check the 3D CoGs. Right, so applications of centroids, distributed loads. There are two principles that we will focus on for this chapter. We will focus on distributed loads on beams, and then forces on submerged surfaces. Submerged surfaces such as your dam walls are the main points of interest. So distributed loads are basically made up of some material, right? So this is snow, right? And it has been building up on this roof. So this is material, it is of a known density, and it is now distributed on top of what? Of the roof. The roof supports the elements or the beams that are experiencing a load on top. But because we cannot be certain that this snow is distributed in such a way that they are exactly 10 kilograms of snow equally distributed on this roof surface, then it means we will need analytic methods to figure out how we can describe this load distribution. So a load distribution is basically summarized by figure 5.17. That's a load distribution. In figure 5.17, we have part A, which describes a load distribution. So the load distribution is basically shown in this axis, where we have some x-axis and some origin. So we have some supports of the beams. So we said we are looking at the load, so that is the load, and we are looking at the beam, which is supporting the load. That's the support of the load. Now, this arrangement that we see is showing us a beam of length L. That beam of length L has some material on top of it. That material is piled up in such a way that at a particular point there is so many newtons of the weight of the material at that particular length, right? So that's at that particular length. Then at another particular length we have another amount of material which has a certain weight. Then the arrangement continues as such, so that in the end we can only describe the weight as a function of distance. So in actual fact, we have a variable called the weight, small letter w, the weight per unit length, which is basically that with respect to the length. Now that we have that weight per unit length, this means that if we are to look at a particular point at which we have some weight. We have that weight, actually let me put it as dW. We have that weight at that particular point, dx. If we are to look at the distribution of this load and try and find the resultant, we would have to first of all add all of the weight per unit length and then find the resultant as the total weight. So how would we find the weight? So basically we would rearrange this equation and write it this way. The small weight element dW is basically given by the weight per unit length dx. The small element dW is given by weight per unit length times dx. So then for us to find the total weight, we would have to integrate. This is why in this equation, I'm not sure what equation number it is, we now find the total weight that is on top of this beam as the integral of the weight per unit length multiplied by the length. I guess you can tell from that equation and from this equation that it makes sense. So that's our integral from 0 up to the length of the beam, from the starting point up to the end of the beam. So there we will now have a total weight. Now, if you look at this setup, there is a very important statement here that we can make use of in the first principle on distributed loads. So it states that we can replace a distributed load on a beam by a concentrated load, right? The magnitude of this single concentrated load is equal to the area under the load curve, and its line of action passes through the centroid of the area, right? So if we are to look at our diagram, what that statement simply means is we can replace this distributed load with the concentrated load. So what we see in part B of that diagram is the load curve representing the concentrated load, and that concentrated load is acting at a particular point P. Now, if you still remember from our previous calculations, you may recall that the center of gravity centroid analog can easily replace our weight with an area. We can replace our weight with an area. Why? Because we know that this particular weight is simply equal to the weight per unit volume multiplied by the thickness and then multiplied by the cross-sectional area. Cross-sectional area. So this cross-sectional area is simply the volume of the material. So for this reason, from that analog that was already calculated or presented earlier, we can easily understand this part where the area is simply representing the weight. So the previous methods are now assumed knowledge. We are now just making use of those. This means that for this roof, there must be a particular point at which the concentrated load acts. And when we are coming up with the structure for this roof, from the experience of these snow build-ups, we should be able to then approximate and say there must be a support beam at this particular location of this roof because of the loading that we experience due to snow. Okay, so now that we have a concentrated load, it's obvious that we need to find the effective point at which it is acting, which is the centroid. So we're just extending the concepts from before, and we're now applying them to a real situation where we are now looking at a load on a beam. So by the same methods as before, we saw that, for example, we had an equation which was like this, where we would find the centroid at which the weight is acting. So that's the center of gravity, rather, if we are using this equation. And we said this is a summation of what? Of the various contributors to this system is equal to 1 up to n. So in the limiting case where we want to find up to the smallest possible element, then we can invoke calculus. So this arrangement has the x bar in such a way that it is represented by what? By the length from O to P. The length from O to P. That is our x bar, which is labeled there. Then that x bar, OP, is multiplied by the weight, and then we get the what? The integral x dw. What are we trying to do? We want to find the resultant, which is the concentrated weight, and we want to find its point so that we are aware that the weight acts at this point, so we need to balance our system in this and that way. So one of the things that we should be aware of is that at every point where we have a support, there will be some reaction force. At every point where we have a support, there will be some reaction forces. So basically, this is just a load curve showing what we have described. And according to this equation, I think we've already seen the analog of changing our weights to areas. So this simply also implies that our OP multiplied by the area is simply equal to the x dA. So we are finding the centroid of this area represented by this distributed load. Right, so an example of applying the principle on distributed loads is in question number 5.66. Question number 5.66 states, for the beam shown, right? Question number 5.66, for the beam shown. So it's loaded, so there's a beam loading. Determine the magnitude and location of the resultant of the distributed load. So you want to find the magnitude of the distributed load, of the resultant of the distributed load, and the location, right? The reactions and the beam supports are the second task. So if we have our distributed load as such, so we can maybe exaggerate this diagram so that we can annotate in a more, I would say, in a clearer way. This is our x-axis, this is our distributed load, this is our small w, small letter w axis, and we have the distributed load arranged in such a way that it increases from some starting point to some end point. And that is straight to our support. So our support is down here. Our support is way down here. I'm just exaggerating it so that we can sort of easily tell what's taking place here. So this is actually telling us something. This distributed load is well arranged, right? It is so uniform that at some length position L is equal to 0, we have a minimum distribution load, and then at some particular maximum we have W, let's call it W max. So in other words, for us to find the magnitude and the location of the resultant, the magnitude of the resultant is basically the what? The weight. So which equation can we make use of? If you remember those equations that we had, which showed us that for us to get the weight, this is simply given by the integral of the distributed load dx, the integral of the distributed load with respect to x. Now that equation is with respect to x. In other words, we need to see the equation of this distributed load with respect to x. What is the function omega of x with respect to x, so that we can integrate it. Now, according to this arrangement, this omega is arranged in the x direction, as we can see, and fortunately in our case this is a straight line. So if it is a straight line, we can find the slope. M is equal to the change in y, in our case the change in w over the change in x. The length, is it given? Yes, there's some length given, so let's just call it L, and then we'll put it there. So what is the delta W? That would be W max minus W min. So let's just call that W naught. Divided by delta X, that would be basically our L minus 0, isn't it? L minus 0, because our initial point is at the origin. So now that we have that slope, this means we can tell that this is not proportional, right? So that will be an integral of the function. The slope, we already know it. I'll just represent it with the m. So that is mx plus c. Our c is omega naught, just because it's a straight line equation. This is being integrated with respect to x. So as you can see, this is a constant, right? So we are going to end up having, and what are our limits of integration? From 0 up to L. So our function will be mx squared over 2 plus omega naught x from 0 up to L, and that would obviously be our resultant. Now that we found our resultant, what is the next thing to think about? The next thing to think about is the location of that resultant of the distributed load. How would you find the location of the resultant now that you've got some number? So this is equal to 1, 2, 3, and this is in the SI system, so this is in newtons. So whatever it is that you got, which is the W in newtons, the question is, at what location is it acting? So for you to find the location at which this distributed load is acting, it means that you need to, let's say if you were to draw it, then you would find that, let's say it's acting somewhere there. Let's just draw the W. So by transmissibility, you can draw it here, you can draw it at the top, it doesn't matter. So that's our W, and that's its line of action. So how would you then find the line of action of this distributed load? So for you to find the line of action of the distributed load, already you can see that it is acting at some distance. Let's call it x bar. It's acting at some distance, x bar. So by virtue of your equation, you remember you also have the equation in the previous case. So you have an equation which defines how you can find the centroid. So that would be your equation from O to P, that's your x bar. It's equal to the integral of what? Of x with respect to W. If you want, you can use it in this format where you've got your x with respect to the area, and you will be able to deduce your x bar. So which means you are just using the same steps as we had before to find these unknowns. So the next stage of distributed loads, besides loads on beams that are on a truck or on some other bridge or such arrangements, we have a lot of work to do with regards to dams, right? So there are a lot of dams that were constructed. Some of them are still standing, some of them failed. But what is most important is to understand forces on submerged surfaces. If a surface is in water or in some fluid, what are the forces that act on it? So to get a picture of how this works, we have figure 5.18. So it introduces us to the orientation of a dam wall and what is called the section of a distributed load of a dam wall. Right. The fundamentals that we still remember, I suppose, from your FEV 101 are that pressure increases with what? With depth, right? Pressure increases with depth. So remember this when we look at this orientation. So this is our dam wall, right? This is our dam. All right, let me just use that color. So this is our dam, right? So that's all our water in there. And this is our dam wall right at the end here. So that's our dam wall. It's built like that. So obvious, its depth is into the what? Into the surface of the water. So that is its depth. If we are to take a section that starts from that point of the dam wall to that point of the dam wall, right? So we have taken a small section of the dam wall and we want to analyze it, right? We can now analyze that section in terms of its cross section. So in other words, we took a slice, right, of that section, and that slice of that section is now showing us from a side view. So this is from this side view how the dam wall is actually interacting with the fluid, in this case, which is the water. So this is actually the bottom of the dam, right? This is the bottom of the dam. which is point B. And this point A is close to the top. So it's not at the top, but it's close to the top. That's our dam wall. The top of the dam wall is right here. So that's the top of the dam wall, which is that point where you can view the dam from. Now, the dimensions we are to consider are supposed to now follow the same format as the format of the distributed loads we learned of earlier. So what we now have is a case where, if you still remember our distributed loads, they just look something like this, right? And we've got our distributed loads, something like that. And this was the x-axis. So into the depth of the dam, we actually have an x-axis. That is what this dx is standing for. So we are at the top of our dam section. The dam section has a depth L, and that depth is along some x-axis. So if we are looking at a small element, we look at a small element dx when we were finding, for example, the weight by integrating the weight per unit length by dx. So these are our values of the weight per unit length, weight per unit length, weight per unit length. If we are to draw it like what we saw earlier, we would draw it like this. We'll draw it like this. So in the end, what you now have is a load distribution, right? But this load distribution is interesting because it's into the depth of the water. At some particular centroid, as we saw from the previous question, we can calculate the particular location where the resultant weight should act. So this is our resultant weight, which is now acting at the dam wall. So it means then that in this diagram, it's acting somewhere there. And this is further down in the dam water, right? Further down in the dam water, and it is pointing towards this diagram. So it's inside the dam water, and it is pointing towards this diagram. So it is actually having, let's say, some tip at that point, which is this point P. That is where we now can use our AP to be the same as the OP we saw in the previous diagrams. Now, so this is how we would apply our principle. In principle, for us to analyze these submerged surfaces, we need to look at the use of the properties of the fluids and the concrete that makes up the dam section, that makes up the water and the dam section respectively. So we already know that our weight per unit length is our small letter W. But we know that if our weight per unit length, if our W is equal to a weight per unit length, right? Our weight is a force. So since our pressure is given as what? As a force over area, then our weight is actually a pressure times an area divided by the length. Now, to describe this dam wall area further, what we can do is we can draw it. Let me just put up a sketch so that we can see the dam section, and it has some depth B. So when we look at the dam section, this is the area that we are discussing. This is the B, which is out of the page on this diagram. It is out of the page on this diagram. Then what we are seeing obviously is just this cross section on this diagram. The area is obviously now this, let's say B. In fact, it's actually this L multiplied by this thickness. Let's call it T. Yes. So it's this L multiplied by this thickness, call this T. That's our area. So this means that in this case, we now have our dam cross section with our P, which is the pressure, and then we are multiplying that by our area. So our area, which is what? If we are to look at it this way, we would use an L multiplied by a B. So that would be equal to an L multiplied by a B times that pressure P divided by another L. So if we were to remove that, that is why our weight per unit length can be described in terms of the dimension B out of the page according to what is on this section, which is just the width of the dam wall, right? Out of the page, and then multiplied by the pressure P. But we already know that this gamma is equal to what? It's equal to the weight per unit volume. So please don't forget that these are not the same. Our gamma is a weight per unit volume. So if our gamma is a weight per unit volume, and we have our pressure written there, this means that our W can be written in terms of the B multiplied by the P. We say the P is the what? The P is the force per unit area. So that would be the weight per unit area. Now, since our weight is equal to gamma times V, so that would be B multiplied by a gamma times V over the area. So as you can see, we can tell that our B would be equal to gamma. This would be area times some height over area, and we have B gamma H. So that's how we come up with B gamma H. So therefore, it's important that when we are analyzing the dam, we remember that our distributed load of the water is in such a form, right? Our distributed load of the water is in such a form. The dam wall has a what? Has a depth L. The dam wall has a depth L. It has a cross section A made up of what? Of the length multiplied by the breadth, which is when we look at this diagram, we would see it as just this B. Let's just say it's in this direction. That would be a piece of the dam wall. Okay, so now that we have that idea, how would we come up in this kind of a situation? How would we come up with the resultant? It's a bit complex when we look at the dam wall fact that it's inside water. So if we look at figure 5.19, it is now giving us an ideal case. So this is the ideal case where we have some dam wall AB. So that dam wall has a resultant acting on it as R. How can we come up with the resultant? We can actually decouple the forces that are acting on this dam wall. We know that this dam wall, there's this resultant that is acting on it. We know that there is some water on top of the what? Of the dam wall. We know that there is some water on the side, which has some force, water on the top, which has some weight, and then we have obviously some water here, which we are applying some forces on. So for that reason, we have part B of the figure 5.19, which resolves the resultant force, or decouples the resultant force into various forces. So just like we said, pressure increases with depth. Remember, we're looking at a curved section of a dam wall, which is this one. So just as we saw in the previous case, pressure increases with depth. So we've got a resultant force due to the pressure, which is called R2. The water on top of the dam has got some R1. The water in the section of the dam has got its own weight, which is this W. Then obviously, as a counteraction to the resultant, we will have the dam wall exerting some force on some section of the water, because behind it is a resultant. That is why we end up having that. So using this arrangement of forces by basically identifying the sections of either the fluid or the dam that are submerged, that are generating some forces, then we can decouple to find the total resultant. So this is how you would use your dimensions of a dam section to find forces on submerged surfaces. So an example is there to show us how we can try this out. So in this example, on forces on submerged surfaces, the cross-section of a concrete dam is as shown. For a 1 foot wide dam section, determine the resultant of the reaction forces exerted by the ground on the base AB of the dam. then the point of application of the resultant of part A, the resultant of the pressure forces exerted by the water on the face BC of the dam. Right, so let's analyze our dam. Because of space, I will annotate the existing diagram. Now, let's analyze our dam. How many pieces of material do we have? We obviously have. We want to find the resultant, by the way. So, okay, so just by inspection, the resultant would, there's some force due to the water there. If the dam is just seated and there's no water, it would have some total weight, and obviously the resultant would be vertical. But because we've got some water with some pressure on its right hand side, then we should have some resultant in the opposite direction of the water, which is a reaction. Then we should have an upward reaction as well to counteract the weight. So basically we should have some reaction in the vertical, we should have some reaction in the horizontal, which would be calculated using your normal techniques. Right, so let's just find out these sections. The easiest is obvious for us to find. I want to find the resultant. So to find the resultant in the vertical is the easiest to find. So how can we find the resultant in the vertical? We can use the principle of equilibrium, because this is in a static case. So the sum of all forces in the vertical must be equal to 0. The sum of all forces in the vertical must be equal to 0. So let's look at the separate sections that make up this material. So we can divide this concrete into some weight. Let's call this weight for the first section. So let's call it a delta section 1. Then we have the second section, which has some weight. Let's just pull it down and call it delta weight section 2. So this is our section 1, section 2, section 3 by the same method. Then that would be delta weight 3. The water, this water that is on top of this section is actually presenting some weight. So that would be delta weight 4. That would be the water, section 4. Then we have our distributed load. So our distributed load would look obviously like that, because pressure increases with depth. So we've got our forces of the distributed load that look like that. And we would have some resultant force. Let's maybe put it in another color and put it maybe somewhere there. That would be our resultant due to the what? Due to the water, right? The resultant due to the water. Now we have all our forces, right? We have all our forces. I think we're happy. We obviously have said that we would end up having a reaction in the horizontal direction. So let's just put it at some arbitrary position and call it reaction in the horizontal, and then we'd have some reaction in the vertical. Who knows where it acts? So let's just draw it somewhere and call it reaction in the vertical. So if you then find its total, we can then find the reaction at some angle. So our equation is looking at forces in the vertical. What are the forces in the vertical? The forces in the vertical, we have a positive reaction in the vertical. So that's a positive force. Then we have a negative W1, delta W1, another negative delta W2, another negative delta W3. Anything else? Yep, another negative delta W4. And these all are supposed to be equal to 0 because we are static. So in that case, then this means that your low-hanging fruit is found by just calculating your reaction in the vertical, which is the resultant reaction. So that's our reaction in the vertical. We've got our weights, so that would be delta weight 1 plus delta weight 2 plus delta weight 3 plus delta weight 4. How can we find the weight? How can we find the weight when we are given their densities, right? So if you are using the SI system of units, then you use the symbol rho. if you are using the imperial system of units, we are looking at gamma, which is the specific weight. Remember, this is specific mass, this would be specific weight. Now, how can we find a weight? How can we find a weight? We know that the weight is simply given by, in fact, we can use the gamma, isn't it? The gamma is a weight per unit volume. So this implies that the weight that you need to find is a gamma times some volume. And how can we find the volume of these different sections? The volume is simply given by the cross-sectional area that we can see, right? The cross-sectional area times the depth, which is the B parameter. So that would be times the B parameter. So they even said that 1 foot wide section of the dam. Right, so now we're happy. We can see the dam wall, we can see its area, and we now know how to determine our weights. So let's look at the first weight element. The first weight element is W, delta W1. So we're looking at gamma of what? Of concrete. So that would be gamma of concrete multiplied by the delta, let's maybe just put B there, B times the delta area 1. That would make up the what? The gamma A, B for the first area element, W delta A1. Do you notice that for all sections 2, 3, we will actually have the same term? So we can actually open a bracket here, plus delta A2 plus delta A3, because all of them are made of concrete, all of them are B wide. The last term that we have is our water, right? So this would be plus the gamma of water, which is simply given as gamma multiplied by B as usual, and then the area is the area, so delta A4. And you can tell the areas are simply, for delta A1 is the area of a triangle, delta A2 is the area of a rectangle, delta A3 is the area of another triangle, delta A4 is the area of that triangle. So you are sorted to make your RV the subject. So it's a matter of now substituting to get your total RV, which is the vertical component. How about the horizontal component? We said that there's some force here that is acting there. So that is the what? The horizontal component. And now we backtrack to our concept of the distributed load. We said that the distributed load, the total force of the distributed load, which we denoted with a W, in this case it will be the area of our water, which we said the resultant force due to the water, because the water is what is exerting the weight per what? Per unit length. So that's the area of our water, and we said we just integrate our W with respect to X in order for us to get our area of water. So how can we find W? How can we find W? If you look at our previous equations, we have already some expression of W. Our W is given by the B parameter multiplied by the gamma parameter multiplied by H. What is H? It is the height, isn't it? It's the height. In our case, the height is actually the depth. The height is actually the depth, which would be an X parameter. So we are basically then integrating our, let's remember that one, it was a gamma multiplied by B multiplied by H. So in our case, it would be X with respect to X. Right, so gamma B times H, which is the depth with respect to X. Remember, in our case, our X is, this is the X-axis, right? So that is the X-axis. So basically, you will need to integrate that. That would be your gamma multiplied by the B multiplied by X squared over 2. And the limits of integration are from the top of the dam, which is at 0, up to the depth, which is at L. So that is this depth. So that is already given as some value there, 18 feet. So that will be from 0 up to 18. And then you've got your reaction in the what? in the x. That would be your r in the in the horizontal. That would be your r in the horizontal, because it's opposing this force, and it's the only force, right? It's the only force. Why? Because the sum of all forces in the x is basically r horizontal, which we are assigning as positive, minus the r due to the weight, and these are static, add up to 0, so they're equal, which is why we can actually use equation, let's call it star, star. Okay, so basically that is your guide to this calculation. If you want to find the point of application of the resultant, obviously you are applying some moments. So you choose some moments about, you choose some point, let's say point, okay, we've got all the forces. Let's choose A as a starting point. Moments about the point A would be equal to what? You have the force due to what? Delta water, delta weight 1, we said here we have a delta weight 2, we said here we have a delta weight 3, we said here we have a delta weight 4. Then we said we have a resultant, right? So we've got some force there, R in the horizontal, right? We also have some R in the vertical. So if you then assign some height value, so let's just call that y bar, and then you can assign some x value, let's call that x bar, then it means you can find your resultant. So when you use that resultant, you can then find the particular point. If you use the moments, you can find the particular point at which the resultant is acting. So that is a summary on how you will work with your forces on submerged surfaces. Now, section 5.4, which is the section that addresses centers of gravity in 3 dimensions and centroids in 3D. It is the same concept. Remember what we did when we were looking at these bodies when they are in static equilibrium, but we are finding the center of gravity or the centroid using areas. This time we're just using volumes, so the theorems are still the same. So in this section we will look at centers of gravity and centroids in 3 dimensions, composite bodies, and 3D centroids by integration. Centers of gravity and centroids in 3 dimensions are the same as what we were working on when we were looking at 2 dimensions. So in 3 dimensions, we are given some rigid body. This rigid body is shown by that diagram 5.20. Let's call this part A. So in part A of this figure, what we see is the centroid of the center of gravity of this rigid body located at some vector position R, and it's in the XYZ plane. So obvious, its weight is given by the magnitude of the weight multiplied by the vector direction, and it's in the negative J. So that's the exciting thing about centers of gravity. We are just looking at the negative J all the time. If we are to look at different elements that make up the rigid body, then we have that element there, another element there, and if we look at the elements, we can now therefore use our equation to find the weight center of gravity. We can use our equation to find the weight center of gravity. But otherwise, if we had just these elements, we would write our total weight, which is the big W. So this is the magnitude. The big weight, the sum of all forces in the vertical, is the big weight in the minus J direction. This is equal to a summation of all the small weights in the negative J direction. So this would be the magnitude of the small weights. The moments about the point O, which is the origin, the moments are given by your R cross F. So this would be your R cross the total weight. And from what we learned, we know that this resultant is actually made of the small contributions. So on the right hand side of this equation 514, we now have the summation of each weight element at its particular position, and we sum the n elements or whatever number of elements. This means therefore that if we play around with our vector algebra, we can move the magnitudes anywhere or the signs anywhere. So if we move our magnitudes, we're just scaling up the whole vector. So if we move our magnitude W and we put it against that R vector, this simply means we have this particular moment and then we've got this minus J as the direction of the vector. So we're just making a cross product of this R vector with this and the magnitude is already given. This is exactly what we're doing on the right hand side. We are just moving our magnitude of the small weight contributions, and if you look at the left and right hand sides, we can actually equate these two, right? Because the minus J is the same as the minus J. So when we equate those two, we have R bar weight, which is the centroid of the weight, is equal to a sum of the centroids of the individual weights. In other words, we are coming up with an equation which describes our weights in the following format: that if we integrate, which is the realistic case, if we integrate those two that we have circled there, we will get a function which is like that, which is in equation 5.16. So this is the method of finding the weight center of gravity of a three-dimensional body. This is the Grail. This is what we're actually studying this module for. So we want to find the center of gravity of a three-dimensional body, so we can now use our integral methods. This was defined all along, so we still remember that, I hope. Then from what we've derived earlier, we know that we can find the center of gravity R bar by just summing up or integrating the R function with respect to the weight. This means therefore we will have x components with respect to x by integrating x with respect to the weight, y component integrating y with respect to the weight, z component by integrating the z function with respect to the weight. But we have seen that for homogeneous bodies, we don't need to worry ourselves. Homogeneous bodies will always have a specific weight. So by definition, we know that for a small element dW, for a small weight element dW on the distributed load, this specific weight can be multiplied by the small volume element, because the specific weight is the weight per unit volume. In other words, this is just defining the specific weight to be dW over dV. So when it is rearranged, it looks like that. And when we look at the integral of this equation, we will obviously get the second equation. The weight is equal to the specific weight multiplied by the total volume. When we have that, guess what? We now have a first moment. So equation 5.18 is the first moment of a volume. We're the first moment of an area, we're the first moment of a line. Now we have a first moment of a volume. So a first moment of a volume is basically given by the equation R bar, which is the three-dimensional vector position. So it's made up of these x bar, y bar, and z bar. So that's how R bar of the total volume is an integral of the R function with respect to the volume. So the centroid of a volume V is basically found by this equation. So this is exactly the same. 519 is just an extension of the previous equations, which were in terms of the area and the length. This time we are looking at the first moment of a volume. So figure 5.19 summarizes the centroid of a volume. However, there are some situations where life can be made easier for us. So there is something called symmetry. We've already investigated it in earlier terms. So you may not find this table in your textbook, but it's part of some text, right? So I think it's very important. So it's now summarized in a table. When we have some body, some volume which is symmetrical, so there's some line of symmetry somewhere. if it has one line of symmetry, then the centroid will be located on the plane of symmetry. Remember, we're now in 3 dimensions. So it's a huge chunk of material. And if we want to, if it is symmetric, right? So let's assume this is a body and it's symmetric. Then this plane that cuts this body, right? This plane that cuts this body. I wish I had something like a plane. So this plane that cuts, let's say I've got a very thick plane. So this plane that cuts this body is the plane on which our centroid obviously is located. So the plane that cuts the body is obviously where the centroid is located. So the plane of symmetry is the point at which our centroid is located somewhere. By the same method, if we have 2 lines of intersection, so we've got a plane, we've got another plane, obvious at, right, so I'll have to put it this way, right, obvious at the intersection of the planes, which is the line of intersection of the planes, that is where the centroid would be located. If we have 3 planes of symmetry, that makes it even easier. Then it means we've got a point of what? Of intersection. So think of a sphere, for example. We can cut it into what? Into all those xy, yz, and xz planes to find the particular centroid at its epicenter. So if we now have an asymmetrical case where we have our material, but we can't find a plane of symmetry, then we can actually find its centroid using integration. So basically, that is how we can analyze 3D bodies. So since we know that there's some regular shapes, which we can take advantage of, this slide is introducing composite bodies, or bodies made of regular shapes. So we can, by the same methods that we introduced earlier, find the center of gravity of a body with some weight W. How do we do that? We can make use of the first moments, or we can make use of the center of gravity calculations. So the center of gravity gives us our x bar. Remember, when it's a capital, now we are looking at composite bodies which you can subdivide into different shapes. So we've got x bar, it's multiplied by the big W, which is just a sum of all your W's. This is equal to the summation of the individual moments of these centers, these weights that make up the rigid body. So we are looking at the x direction, then we look at the y, and then the z directions separately. That's equation 5.20. If we use equation 5.20, it means we can find the actual centroids. So the x position of the centroid, the y position of the centroid, the z position of the centroid can be found by just dividing those. Right, so using first moments principles, we know that the weight in this case is now, we can use the volume as the analog of the weight. So if we can use the volume as the analog of the weight, we can find the centroid. Remember, these equations will only work if this material is homogeneous. These equations only work if this material is homogeneous. Otherwise, if it's not homogeneous, its centroid does not coincide with its center of gravity. There will be different points. So there we have it. It's exactly in the same format. We're just replacing our weight with the volume. So we've got our volume there, and then we've got our x bar v, which are the summed up volume elements, or the small, we can call them delta volumes. The same applies to the y and the z, so that we can get the centroid x bar, y bar, z bar. So if we do not have density information about this material, but they just told us that it is homogeneous, it means we can simply use equations 5.21. Right, so these are just examples of some shapes that are provided for us for our study in the tables. So we have, for example, a pyramid. The pyramid, we have symmetry, right? If it's a pyramid, we have symmetry. Our only point of concern would be the x position, which is where we need to find the centroid on. So that is our pyramid. It has some dimensions A, B, and that is the label of your centroid. So it's very important with these diagrams for you to identify the correct orientation and identify the A and the B and so forth. Because the equation for your centroid, for example, is just h over 4. So we're already given in tables, right? You don't have to start to calculate it. So if it's h over 4, then you need to identify that as your h, and your volume is given as a third of ABH. That's your A, that's one dimension of the pyramid. That's your B, that's the second dimension. And that's your H, which is the third dimension. So there we have our pyramid. If we have a hemisphere, its centroid is located from its base. The same applies. This one was located from its base. So if the diagram is such that it is starting from that, then you need to be careful. So by the same methods, you need to find what your A is, which is a radius, and you will also use it to find the volume. So that is basically a summary of the centroids of regular shapes that are in 3 dimensions, which we call the 3D rigid composite bodies. So an example is shown in question 5.96. Consider the composite body shown in that figure. Determine A, the x bar, the value of x bar, when h is equal to L over 2, and the ratio h over L for which x bar is equal to L. So if we want to find the x bar, fortunately in this case we have symmetry. How many lines of symmetry? We have how many planes of symmetry? Sorry. We have a plane of symmetry at this orientation. So this would be the what? This would be the XZ plane, right? This is in the X axis, this is in the Z axis. So the XZ plane, when it is offset half A, it becomes a plane of symmetry, right? So we're happy with some plane of symmetry there. We can actually follow it all the way to the tip, and it goes onto the other side. So it slices this object. This means that our centroid already has its x bar. We don't know it yet. That's what we are looking for. But we know that its y bar is actually, so let me just write y bar, z bar. So its x bar is what we're looking for. Its y bar, we've seen that it is at half of A, because our A is offset from the y is equal to 0. How about z? Z, now look at the other plane. So there's this other plane which cuts the pyramid. So that's right there, right? There we have it. So that plane that slices the pyramid at what? At z is equal to b over 2. So that would be half of b. That is the second plane of symmetry. So where they intersect, which is the line that passes through this. So it's a line parallel to the x-axis. This line is at this offset position, right? At this offset position. That becomes our line of what? Where the centroid must be located. Therefore, we are just looking for an x position, right, along that line. So I'm just taking a second axis and I insert it into this particular point. I insert it into that particular point. Now I have a line on which the centroid is located. So we are happy now. We now have our setup. We can tell that we can find the line of symmetry of this object, a plane of symmetry, an intersection, and then the centroid. So let's now look at finding x bar. How can we find x bar? We had principles that we introduced earlier. We know that for us to find our x bar, this is a regular shape, so I will use a capital X bar multiplied by what? By volume. This would be equal to the summation. So that would be the summation of x bar I delta volume I is equal to 1 up to how many? We've got one object there. We've got the second one is a pyramid. So up to 2 objects, right? Now let's decompose. What is the x bar of the first object? The first object is what? It's just a rectangular prism. So if it's a rectangular prism, its x bar, I think it's a no-brainer. It's just half of L. So that's half of L. Are we measuring the half of L from the origin in the x-axis? Yes. We are looking at this distance, right? So it's half of the dimension L, which we found there. So we're happy with this first parameter. What is the volume of that rectangular prism? So it's obviously your length times breadth times the height. So our length in this case would be our B, our breadth in this case would be our L, and then our thickness would be our A. So that's our first term. Let's look at the second term in the x direction. What is the location of our x bar for the second object? The second object is a pyramid. So if it is a pyramid, let's look at the pyramid. Fortunately, we have something here already for the pyramid, so we are happy. So we've got an h over 4 for the pyramid. An h over 4 for the pyramid, that is the x bar. According to this diagram, the h over 4 is being measured with this as the as the origin. So we will need to find our origin, and then we know that h over 4 will become our centroid. In terms of orientation, our pyramid is oriented in the same way as in the text, so we are just going to use the L plus the h over 4. Fortunately, this is also h, not really fortunately, coincidentally, right? So it's just the same label as we had in the table. So that's our location of the x coordinate of the centroid on the pyramid. What is the volume of a centroid? What is the volume of a centroid? Without having to struggle, you just pull the tables. A regular shape, a third of ABH. What is A? These are the base dimensions and the height. So basically all the dimensions there. So that's a third of, what is the base of this? We've got an A, and then what is the other one? It's a B over 2, and then what is the H? It's an H. So there you have your parameters. So the parameters on the left hand side would obviously become what? X bar multiplied by, what is the total volume? So the total volume, we are adding this volume to that volume. So we have our ABL plus, this is a sixth now, isn't it? A sixth of ABH. A sixth of ABH. This is equal to this whole term. Let me just rewrite the summation because I'm sure you already know what is happening there. So if you then use the rest of your algebra, then it means here all you want, according to this question, is to now the value of x bar when h is half of L. So in other words, if you replace this h on both sides with half of L, you should be able to find the wanted or the required quantity. The ratio h over L for which x bar is equal to L. So that ratio is obviously something that you can come up with when you have the total expression, right? Then if you want to find that ratio, you are merely using your algebra. I think that you will use the algebra at this stage before you formulate, so that you can find the ratio h over L for which x bar is equal to L. Right, so remember you already have your expression for x bar before you substituted L is equal, h is equal to half. So just remember that in part B, the ratio that you want to find is where your x bar is equal to L. So you equate your x bar to L, then you just work around the algebra to pull out h over L. Right, so that marks the end of composite bodies. The last section is on volume of centroids by integration. So remember, we said when we have some objects that are not symmetrical, then we will need to figure out a way of building these. So by the same method of the first moments, our definition of the first moments was already given, so you know it now, and I will not waste your time. So the first moment of a volume x bar v is given by the integral of x dv. In this case, we are now integrating an x bar of the strip or the element. The second is the y bar v, the third is the z bar v. So immediately think of symmetry when the object has some lines of symmetry. So in this example where we are now constructing a volume element, you can tell that there are some lines of symmetry on the y bar and the z bar axes. Now, let's identify the what? The x element. Let's identify the y element. Let's identify the z element on the volume element. Now, the volume element, basically just look at your algebra. Sorry, look at your geometry. So the geometry is what will guide you as far as a suitable volume element is concerned. In this case, the writer chooses to use a volume element that is along the length of the cylinder. So this is a cylinder in figure 5.22 where you're identifying the volume elements. So by the way, we want the x element, the y element, the z element, and obviously a definition of dV. Then we are good to go. So what is x element? So look at the arrangement. This is your x-axis. This is your y-axis. This is your z-axis. So obviously your x element is positioned at some x position. So this is along the x-axis. So if I could extend this x element line onto this, is obviously some x, which is why we have the x element simply given by x. How about the y element? The y element, we look at the y element. So this is what we are looking for. Along the y-axis, it's basically, if we were to extend this, this is some value y. Therefore, our y element is just a y. How about the z element? The z element, we obviously now look at this point. In this case, it's half the height. So that's why it's z over 2. What is dv? It's just this geometry of the strip. It is it's a rectangular prism, isn't it? Yes. So it's a rectangular prism. So it's a square that has been extended in length. So it makes up a prism. So it's obviously length times width times height. So what is our length and width? dy and dx. What is our height? z. So that is why we have z dx dy. So therefore, we can use, let's say, the equation x bar v is equal to the integral of x element. We just take that x element. So let's just write this equation maybe. X element, that's an x, dv is z dx dy. So if we do not have a z as a function of x or y, it becomes a constant. So for example, it would then look like this, dx dy. But you just need to be careful with your diagrams so that you are aware if or not you have a constant. So basically that is a volume integral. You can also choose another element, which is a disk. So you can choose a disk. So we can do it like that and say that would be our element. So maybe it's in there, something like that. This disk would obviously have a dz as its thickness. It would obviously have some radius, so that is its radius, and obviously your radius can be related to what? To the x and y components. So in other words, you can then find your z element is obviously now just the z position. The x element, you now know that you can find your x element using your r and your theta that makes up the disk. So you can choose an element of your choice depending on what's closest. Then if you are to determine the centroid of a body of revolution, all you want to do is to declare a volume element. So we are just doing the same thing, but we are doing it in a different geometry. It's not the cylinder that we had. So we just have a disk. That disk has a what? Has a thickness dx, and it has a radius r, and that r obviously should be related to this function, right? That function which is let's say in the xy axis it would be a function y as a function of x. So basically that's what you have. Your x element is just an x position. Your dv, what is your dv? What is your small volume element? It's obviously cross-sectional area times what? Times thickness. Cross-sectional area is pi r squared. Thickness is what? Is dx. So you can now determine your volume of integration. So just for us to see something that may be relevant to this, I just want to pull out a graphic. Let me just see if that is going to work for just a moment. So in Chrome here, we just show you something from, so this is courtesy of Dr. Lou Talman, Department of Mathematical and Computer Sciences, Metropolitan State University of Denver. So they have some interesting graphics here. I'll just explode this so that we can see. So this is a plane region, right? This is a plane region, and you can then find the volume of the region by integrating. So that is Papascaldinas. Our exercise is to now find the centroid of that volume. So we did use Papascaldinas, but we are now interested in the centroid of the volume generated by Papascaldinas. This means that for these exercises, you are going to need to make use of both Papascaldinas theorems and your usual integration to find the centroid by the centers by the volume of revolution. Okay, so we just have another geometry there, which is a plane shape that is forming a very nice 3D volume. And then we also have this one, which generates a jug, right? So you can integrate, you can choose whichever way that is going to be useful or easy for you. Remember, the most important is the function, right? There must be a function that generates this net that then gives you a piece or a volume of integration, or the volume element. So basically that summarizes the volume elements that you find or that you can use to find centroids by integration. So let's see an example. 5.125. Locate the centroid of the volume obtained by rotating y, the shaded area, about the x-axis. So we're rotating this about the x-axis, and we're getting some, it's going to be a volume, right? So it's not a mug, right? Maybe I'm hungry, I'm thinking of mugs and a cup of something to drink. Okay, so our equations already gave us the format. We are going to use our x bar, v being equal to the integral of what? Of the x element multiplied by dv. So let's have a definition of terms now. What is our x element in this case? So we need to you need to picture the volume, right? You need to picture the volume. So for example, we're drawn something like this. So this is going to be our volume. If this is going to be our volume element is therefore defined by a disk. So it's just that small disk, something like that. And then we can put some dots to denote that that's the interior part of the disk. It will have some radius, obviously, from this axis, and that radius goes to this y. In actual fact, its radius is actually y, right, from what we can see there. So we now have its x element is obviously given by just what? By just x. So that's the x position from where? From the start position. So that's our x element of the strip. Then what do we want? X element, we now have it. What do we want? We want dv, definition of dv. So a volume is simply equal to, a volume element is an area times the thickness. So that would be pi times the radius squared times the thickness dx, because it is dx thick. That's dx for this volume element. So this means we now have all we need, because as far as, for example, the left-hand side to get our volume, we can just integrate our dv to get the volume. So that would be an integral of pi. We can tell that the radius is just a position from 0 up to the line. So the line is already defined as y. So I'll just write this as y squared dx. That would be your volume. From where? From x is equal to 1 up to x is equal to 3. That's your integration along the x-axis. So we now have our definition of terms. Let's just rewrite this. So I will write our x element. So that's an integral of x multiplied by dv. What is dv? Pi r squared. So that's pi y squared dx. Pi y squared dx. From where? From 1 up to 3, isn't it? Yes, from 1 up to 3. So there you have your equation. You have the v already from the previous determination, and then you can carry out your integration. Remember, your y is a function of x, right? Your y is a function of x, so your integral will simply be from 1 up to 3 of what? So your pi is a constant, it's out. X multiplied by the function 1 minus 1 over x. So that's a 1 minus 1 over x. And we are going to square that with respect to x. When you do that the same way you did, you need to do it there, then you can find your integral. So obviously this is different from what's on the left hand side. Let's not have the temptation, right? This integral has an x multiplied by the function, but the integral on the left hand side for this volume is actually x bar multiplied by the integral from 1 up to 3 of just dx. So it's so we've got our pi, and then it multiplies by what? Y squared. That would be 1 minus, so that would be 1 minus 1 over x all squared dx. So let's not think that then we can easily remove that. It's tempting sometimes, you know. So basically that's how you would analyze your objects to find the centroid by integration, as long as the object is not a regular composite shape, and then you cannot use those tables. So project number 5, apply equation 5.23, right? So apply equation 5.23. I hope you are trying out these projects. I'm not going to mark them. It's just for us to see if these things are actually sinking. So apply equation 5.23 to verify project 4. Remember project 4, right? Just look at the text for project 4. You were supposed to use Pascal-Dinas to verify the volume of your mug. So now to verify project 4, now you are using equation 5.23. So if you look at equation 5.23, this is what we have here. So it is actually giving us the centroidal positions of your mug. In other words, you can actually use this volume element of your mug. Let's have the definition of the volume element. Where was it? There was a definition of the volume element somewhere. Okay, I can't see it, but I think okay. So maybe you can just use the definition. There we are. Sorry. So there we are, because your mug would look like what? Would look like this cylinder. So just use your equation of the volume element to determine the volume of your mug. So it means you now have 3 methods. You have Pascal-Dinas, right? You've got the experimental method where you're going to pour out your fluid into this one. That one is the one which we're happy about, because we know that measuring cylinders are checked by standards. The South Africa Metrology, NM Metrology Institute, National Metrology Institute, NMI, yes. They check all those things, so they can't sell us measuring cylinders that are wrong in the shops, right? So we will use that measuring cylinder or a measuring mug. You've got your mug, you put your water. Experimental method says, okay, your mug is 200 mils in size. When you have that, then you will use Pascal-Dinas. You've got your area. You can put an area or a line of symmetry. Then you can calculate the volume. Then you use your volume element and you integrate and you see how it goes. So basically, this sums up our chapter 5 of this statics module. So now we have crossed over. We have finished all the sections that give us the fundamentals of what we will need to use in the dynamics module. The next chapter, chapter 9, is going to be slightly demanding. It will have quite a lot of things to work on. So it will actually have 4 lectures. So it's important that we make sure that we have attempted the practice tests. Remember what we said when we started. Let's not wait for the time of the tutorial test or the time of the semester test. Please work on the practice tests as we study. That's the only way you can end up coming up with questions. I'm hoping to actually see a lot of questions in my inbox that are based on what we're doing here, so that we can verify if this is making sense. You're going to need to use all these concepts in your studies, so and in your designs especially. So I just hope that you are doing some work and actually making use of these equations to solve for the unknowns. So this is the end of our chapter 5. Let's meet tomorrow when we will study chapter 6. All the best and enjoy. Have a good day.